Okay, hi everyone. This is just a video on the second law of thermo, and I'll describe heat engines, refrigerations, and heat pump cycles. Okay, so here it is. Outline. Introduction to the second law. Talk about thermal reservoirs. We're going to talk about heat engines, thermal efficiencies, refrigerations, and heat pumps, and reversible and irreversible processes. So if you remember from the first law, all right, it tells us the amount of energy being transferred, but it doesn't tell you which way. We just know energy is conserved. The second law tells you what direction. So a cup of hot coffee warms up the room. It doesn't get hotter in a cool room. The room is heated by the wire, not the heat is generating electricity. All right, so the second law may be used to identify the direction, and I'll talk about that later. What are thermal reservoirs? Well, they're basically a source that supplies energy in some form of heat. All right, so a thermal energy source, okay, does that. Where a thermal energy sink, absorbs energy in the form of heat. So you have a source and a sink. Cyclic devices. Basically, it's a system that goes through a series of processes. So if we look in the bottom left here, it goes from 1 to 2, 2 to 3, 3 to 4, and then from 4 to 1. It completes a cycle. All right, and this is what we call an Otto cycle or a diesel cycle. Here's the refrigeration process. All right, it has different processes involved in here. So let's look at first a heat engine, and the easiest one to look at is a steam power plant. So this is the schematic of a steam power plant. You have a pump that moves the liquid around, or the fluid. You have a boiler. You have a turbine that extracts energy out, and you have a condenser that heat goes out to the sink. Okay, so a boiler produces energy. So you supply energy in. The system boundary is the entire system. So this is how we write it in terms of a simple schematic. You have a reservoir at a high temperature, TH. We supply energy into the cycle, the heat engine. We get work out, and we have some Q out that goes to a sink. So if we do the first law on this, it's a closed system. The entire system doesn't change temperature, so delta U is 0. All right, then we have Q minus W net. Now again, this is slightly different than what I've been telling you. These are equations right from the book. Just remember that this W net is out minus in, not in minus out, because you have the negative here. All right, so in this case, what you do is the difference in Q minus Q. Okay, let's see. So basically, what we have, again, for a heat engine, I'm not sure if that got recorded, but I'll do it again. So we have a high temperature reservoir, goes into the heat engine. We have network out, and some of the heat goes to the sink. So when we do the energy balance on the heat engine, we have QH minus QL equals the network out. All right, so heat engines. They convert heat to work. That's the bottom line. Remember that. All right. They convert part of the heat to work. Some of it has to be rejected, and they operate on a cycle. Okay, so let me explain why we need to release some of the heat. All right, to make it. So here we have a reservoir, supplies heat into this piston. It moves the piston up with the load. Now, in order to get this down, what do we have to do? Well, we have to release some of the energy to decrease the temperature to move it down. All right, so if we didn't release some of this energy, we wouldn't have a cycle. All right, it wouldn't work. Because if we extracted all this energy, first off, then we would have no energy left to keep going. All right, so we always have to want continuous motion. So we always have to release some sort of energy in order to get it back to where it was originally. So let's talk about thermal efficiency. It's network output over total heat input. So for a thermal efficiency, we have network out over Qn, because that's heat input. And then you can we already rearranged this. So before in the previous slides, we have 1 minus Q out over Q in. Or the efficiency, you can rewrite it as 1 minus QL over QH. Okay, so let's talk about refrigerators. Okay, so here's a schematic of a refrigerator. You have an evaporator, okay, and basically this is the air in your fridge. So say it's hot, and that energy then goes to the evaporator to warm up the liquid that's in here. So then it cools the air in here, and the liquid comes around to a compressor to get the fluid moving. All right, the liquid. Then it goes to the condenser, where some of that heat energy then is taken out to the kitchen air. And then we go to an expansion valve to decrease the temperature so it's cold, so the air in the fridge can then warm up this food liquid and then go back and around. So that's how refrigerators work. Here, so we don't talk about thermal efficiency. They just use coefficient of performance, which is desired output over required input. And what we want to do is we want to get that Q. So that's our output. All right, and we need to supply some compressor work in. All right. So here we have a compressor. The coefficient of performance of this refrigerator is QL over QH minus QL. All right, and again, this comes from the first law. And I have hand notes that I posted on Blackboard that should help you clear this up too. Heat pumps. Basically, heat pump is basically you have very similar to a refrigerator, but they're just kind of flipped. All right, so the work supply to a heat pump is used to extract energy from the cold outdoors and carry it into the warm indoors. All right, so very similar to a refrigerator, but basically they're kind of just flip-flop. Just rotate the fridge around. Okay, and it's just coefficient of heat pump, QH over QH minus QL, or it's equal to the coefficient of performance of refrigerator plus 1. So again, it's just like flipped of a refrigerator. All right, it's a little side joke. Okay, so reversible and irreversible, really all I want to talk about is basically you have reversible processes that can be reversed without leaving any trace on the surroundings. An irreversible process that basically if there's friction, if there's heat transfer, if there's sound or chemical reactions, you can't get that back. So like heat, if you have a hot environment and you have a cold soda, it's going to heat that up. You can't get that heat back because there's just no physical possible way unless it gets colder out, but it's not the same. It's not going to be the same because you heat up the soda and then the soda can't then extract that energy back out because it's going to be in equilibrium. All right. Every process is irreversible, but we assume a lot are reversible. Okay, they're easy to analyze and they serve as ideal models. Just to give you an idea, basically, the higher the temperature in your reservoir, the higher efficiency you're going to get. Okay, and then in the last few slides, I just provided with you some examples that you can take a look at. All right. Plus, I posted 3 examples online, and it should be enough. My next video will talk about a Carnot cycle.